All right, we're going to do a quick mic check first and then get started.
Here. Worst idea ever. Everybody's going to try to come here.
All right, so this is UAV's Hydrophones webinar. I'm Ian Thompson on the electrical team. So this one's going to be a bit different from all the others in that our other webinars have been more about general ideas of how to run the team or how to do things on the team. In this one, I'm going to go into a lot more detail on specifically how you implement the hydrophone system. And since I don't really want to go into detail on a system I don't know about, I'm going to be focusing primarily on our system and how we do it. I guess we can get started. So of course, the hydrophone system, its goal is to complete the pinger task in the RoboSub competition. So you've got hydrophone elements in the water that measure acoustic signals, and those get read by hardware and then processed to perform some things. So of course, the requirements for that measurement hardware is driven by what sort of measurements we need. In our case, our system requires that we have 3 elements in the water listening in the 20 to 40 kilohertz range, since those are where the pingers are. So our hardware is designed around that. We have 2 primary modes for our system. We have what we call search mode, which is for, we don't know what the active pinger is yet, so we have to go find it, or we have to find what frequency it's on. And then once we identify the frequency, we go into what we call track mode, which determines where we need to go to get to the pinger. And again, this is our system. There's a lot of other ways that it can be done. I know a lot of teams work by measuring the delay in arrival of a ping between different elements. We actually don't do that. We have elements very close together instead, and measure the difference in phase between the signal arriving at them. So before I dive straight into it, I want to make sure that I have a couple definitions out of the way for those less familiar with signal processing. So first and foremost, the most important thing here is the Fourier transform, where you take a signal from the time domain and compute it into and convert it into a set of frequencies. So those frequencies, when added together, will produce the original signal. And this permits you to think about signals rather than as time, just as the frequencies, or isolate a certain frequency out of a signal. So for instance, you've got a pinger at 23 kilohertz. You can look at just the 23 kilohertz component of the signal to find out stuff about the pinger itself. And ignore any other noise like the diver running around or your thrusters making noise in the water. And there's a bunch of different kinds of Fourier transforms. So the discrete time Fourier transform takes in takes in signals as a set of discrete points in time, but outputs the result at any frequency. So you give it a certain frequency that you want to know about, and feed it in a set of samples, and you will get the component of the signal at that frequency. In contrast to this, there's the discrete Fourier transform, in the most confusing name possible, wherein you input data in discrete time, but you also get frequency out as discrete frequencies as well, where you just get bins of frequencies collapsed together. This is useful in cases where you don't know exactly what frequency you're looking for. You want to analyze a bunch of them at once. And for most cases, this is the one that computers use. And there's a category of DFT called the fast Fourier transform, or FFT, which is any DFT which can be computed fast, where fast in this case is in n log n time for any of you computer scientists out there. So I've been talking about sampling, and the first thing, of course, when you're talking about sampling is how fast you need to sample. So when you're processing signals, you're limited by how fast you can take samples. If you're sampling too slow, as you can see in the image above, you'll actually get other signals called aliases that appear on your result. And those are, of course, unwanted and will produce bad data for you. So you need to know what frequency you need to sample at. And this was worked out by someone named Nyquist. And he basically found that you need to sample at least twice the highest frequency that's in your signal. Note that this is not the highest frequency you care about. This is the actual highest frequency in the signal. So if you care about the 23 kilohertz signal, but there is a component at 100 kilohertz, you still need to be sampling at 200 kilohertz. So that's basically the theory that needs to be covered right now. So I guess we can dive into actually how do you build a hydrophone system. So you've got your set of elements. In our case, we have three, the reference element, and then two elements, x and y, offset in the x and y directions, of course. And because we're measuring phase, we need this reference element so that you can have a reference, you can have a zero phase. And you also want to make sure that your elements are spaced the same distance apart. If they're not, then you've got to do all sorts of fancy math to resolve that, resolve the effects of that. And it just gets complicated. It's a lot simpler if you can make sure that your elements are spaced equally apart. So you have your elements, and then those generate a voltage. So you pass that voltage into an amplifier, because that voltage is too small to be read by most things. And in our case, that amplifier is 10 times gain. That'll vary depending on what elements you're using. And then because of this problem with high frequencies causing aliasing in your signals, you have to put it through a filter to make sure that the high frequency components don't exist when you start sampling at your ADCs. So we have a bandpass filter. This is a type of filter that cuts out both frequencies above a threshold and frequencies below a different threshold. So you get just a certain range of frequencies in your signal. So you have that. You now have your filtered signal. It contains frequencies ideally only where the pingers can be. And so you feed that into ADCs. For this stuff, you generally want good ADCs. First of all, they need to be able to sample fast because you're dealing with high frequency signals. But you also want them to be accurate. So ADCs have a number of bits that they measure. You can get, like, some microcontrollers will have 8-bit ADCs. The ones we're using are 12-bit. Generally, larger is better, but there is a point of overkill. Yeah. So you've got your data in your ADCs, and now you've got the sampled data, and then you take it to some sort of processing chip. And that's where all the actual magic occurs. At this point, you've just got a wave of noise, and then the digital processor is what actually takes that noise and turns it into a heading that you need to go, or the frequency that a pinger is at. So in addition to the temporal aliasing that I mentioned before, there's also an issue of spatial aliasing. So you can think of it as you're sampling in time in the temporal case, but when you have multiple elements measuring, you've got sampling occurring in space as well. And so you also have to take into account aliasing that can occur in this. So I am really sorry for that lambda that got mangled for some reason. I have no idea what happened there. So spatial aliasing, temporal aliasing is based off of frequency, while spatial aliasing is actually based off of the wavelength, which varies depending on what medium you're in. So if you're in air, the wavelength is a lot smaller than when you're in water. This is actually good for us because it means that, for instance, if you're listening for a 40 kilohertz signal, the wavelength that you have to worry about is only 8.6 millimeters, which means that your elements would have to be sitting 4.3 millimeters apart, which for most mechies will make them cry, and nobody wants to seal an enclosure with things 4.3 millimeters apart. But in water, because the speed of sound in water is so much higher, the wavelength gets a lot larger, and so you now have the wavelength is at 38 millimeters, so you can put it about 20. You can put them at 19 millimeters apart, and everything will work fine. And then mechies rejoice, and sub is watertight, and all is good. Yeah, so you have to remember that this is half of the wavelength, not the full wavelength. If you get that wrong, you'll lose about half of your range of frequencies. So then you've got the digital processor. There's actually a lot of different ways you can go about this. We've got two systems that we've used. The current one that's been in use for the last 5 or 6 years is a Analog Devices Sharp DSP. It's a fairly high-end chip that does Fourier transforms in hardware and is designed exactly for this purpose. Unfortunately, it's somewhat expensive. The chip itself isn't too bad, but the programming tools are very, very expensive to license. And we haven't really had a great time debugging this sort of thing. We can't really get data off of it so that we can actually look at what's being heard in the hydrophones. So to combat this, we've been experimenting with using a ARM microprocessor as a drop-in replacement for it. So you can get these really cheap. They're really easy to program. There's information everywhere about them. Google knows everything. And we've actually been finding that they're also fast enough to do all the processing that we need. So the algorithms I'm going to show you later is very computationally light. And because it operates on each sample individually and doesn't need to go through the full history of samples, you don't really have to do too much processing to do the calculations. And then it's got, if you go to the ARM processors, you've also got some nice features, like you can connect them over USB rather than going over serial, so you can actually transfer data. You could, in theory, transfer all the data out of the hydrophone straight to the main computer and do the processing there. So if in case that you don't have enough power inside your system to do that, or to do all the processing, you could do it elsewhere. We're still experimenting with this. We haven't quite gotten it working yet, so your mileage may vary. But it's looking promising, and if it all works out, it means that it's a lot cheaper and easier to build a hydrophone system. And really, your biggest cost then comes down to just the elements themselves. So when it comes to designing the hardware, again, you want to make sure that you've got your sample rate good or correct and high enough. This is primarily controlled by your ADCs. So an ADC will have a certain sample rate that it supports, generally measured in kilosamples per second or megasamples per second. Part of this is also dependent on your whatever control processor you're using, since it has to actually initiate the sampling. So you have to have something that's capable of pulling data in fast enough from the ADCs. You also need to make sure that you get your element placement correct. The elements need to be placed very carefully, especially in our system, because we are very sensitive to phase shifts. So if the element is off of its position by any significant amount, then that's going to show up as an error in our heading. This also means that when you're selecting elements, the size of the element does actually become a concern. As if it's a very large element, you won't be able to get them close enough together to meet the spatial aliasing requirements. This also is when you're dealing with just putting it all together, laying out the hardware on the board. The phase shift requirements mean the phase sensitivity means that you have to be careful to keep your cable lengths similar. You don't have you don't have one signal taking a longer path throughout the board than the others. You just have to be generally careful. I don't think these issues exist as much in systems that measure based on the arrival between far spaced elements, but it's still a good idea to make sure that everything arrives at your processor at the same time. And then, as I mentioned earlier, you want that bandpass filter to make sure that you don't get temporal aliasing inside your signal. In our case, we filter such that we only get 18 to 52 kilohertz going into our ADCs, and that's a fourth order Chebyshev filter. There's a lot of tools a lot of resources online for figuring out how to build these filters. I know Linear Technologies makes a tool that you can just type in the frequencies that you want, and it'll spit out a schematic for you. So there's a lot of things that you can find online to design these. And because there's some really strict timing requirements in here, you need to make sure that you're sampling at exactly the right time and that you can process the samples in time before the next sample comes in. You probably want your processor to be dedicated just to the hydrophones. You don't want to be sharing it with, say, running your thrusters or something, because the thruster controller could inject noise into your hydrophone system that you don't want, and also it's just there could be a chance that the processor is too busy dealing with something else and doesn't sample in time, which means that your processing gets thrown off, of course. So that's a basic overview of hardware. Then I'll move on to the actual pinger tracking. So we're given a pinger frequency, and we want to know, based off of the signals that we're receiving, what is the heading to that pinger. So that triangle pattern that I showed earlier was designed explicitly for this, so that we can measure the difference in phase in the different directions. And so I'll leave this as an exercise to the listener, but you can go through the math of what the phase shift will be depending on different headings or different incoming headings for the signals from the pinger. And you basically come out to the heading is the inverse tangent of the difference in the phase on the Y element over the difference in phase on the X element. So that's nice. You know how to take a phase, how to get from a phase to the heading, but you still need to get to the phase. And so to do that, we use the discrete time Fourier transform, DTFT. So this algorithm outputs a complex number whose magnitude, if you look at this complex number in a polar form, the magnitude of it represents how strong the frequency is, and the angle of it represents the phase of that frequency relative to some arbitrary reference. And so if you make sure all of your DTFTs use the same reference, then you can subtract the phase of the reference element from the phase of the Y element, for instance, to get the phase difference between those two elements. And one of the DTFTs is that the computation is completely iterative. So you just make a slight modification to the result based off of the new sample that comes in, and everything is processed already then. So here's the formula for a DTFT. This is the general form that you'll find in basically any textbook or Google. You'll notice you've got the capital X means frequency form of the signal. You've got it's a sum of samples multiplied by a complex exponential, which is basically just a sine and a cosine. I'll get to that in a sec. One note is that because I'm an electrical engineer, rather than using I, which in most cases means current, I use J as the imaginary number. So a slight problem here is that this formula uses infinite time, and infinite number of samples. So it goes back to the beginning of time and goes forward forever, which of course is a problem because we don't yet have the technology to see into the future, and also you don't have enough memory to store all the samples in history. And then there's also the issue that even if you did get a very large range, you wouldn't want to use such a large range because that wouldn't tell you specifically, is there a ping going on right now? It would just tell you that there is a pinger in general. So to deal with this, we instead take a small window. So you start at some sample and then you get the next, L samples. In our case, we do a length of 256. Somewhere around 128 samples. The number can actually vary a bit. But there is actually, this does make some slight changes to the result that I'll get into later. But for now, you can just assume that this is effectively the same, but looking only at a smaller range. And then you've got this complex exponential here, but you can actually just expand that into a cosine and a sine. And once you do that, it's fairly easy to compute. Almost every, basically every library has a cosine and a sine function. And so you can just compute this for each sample that comes in, and the result is fairly good. One thing is that when you're implementing this, rather than like you've got the sum, so you still have to take the sum over 256 samples. You can actually bypass that by using a ring buffer. So if you keep a buffer of the last 256 samples and just maintain the sum, you can actually just subtract the old sample from the sum and add the new sample to the sum, and you've done all your computation for the DTFT on this sample, which is nice. It means that the processor load is very low, and you can go to a higher sample rate. So here's some admittedly fake ping data. So we've got random noise coming in, and then here's a ping. And on this and all future images, the red area is the same in all of them. So you can tell where things are relative to each other. So in this case, the green area represents the portion of the signal that's used for actually recognizing the heading. You'll notice that is very small. Our method means that we can take a bunch of samples and average them together. We don't depend on seeing just the rising edge of the ping like time delay systems do. And then the red area is the dead time. So it's an area that it recognizes that it's still a ping, but we don't care about it because it's not, because we already grabbed a heading from this ping. If you wanted, you could continue measuring heading throughout all this and and using that to make your results better. So you've got this ping, and there's a spike, but it doesn't really tell you much. But when you, and this is from only one element, but when you take the three elements together and do the arctangent that we did earlier, you come out with this, which is the actual heading to the element, or to the pinger, which is nice. You got a fairly flat line there, and you've got noise elsewhere. Unfortunately, you have noise everywhere else. So actually identifying this heading is like finding a needle in a haystack. So you want to have some system to identify exactly what is a ping and what is just random noise. Because if you were to continuously read headings and try to find places where it's stable, you get basically every heading in the book. But you also have this magnitude data that came in from the DTFT, and that's shown in the lower left corner. So you notice that the magnitude actually is the magnitude during the ping is very high compared to everywhere else, where it's basically 0. So you can use this as as an indicator that there is a ping going on right now. Another indicator we also use is the variance on heading. So part of this is just to make sure that even once the ping starts, that the heading result we're getting is stable. And once we get below a certain threshold in variance, that means that our heading results are stable, and this is most likely an actual ping. So with that, you can identify what is a ping and what isn't fairly easily. These are actually the only two sources of data that we use for ping identification. And it seemed to work fairly well for us. So the thing that I glossed over earlier about the effects of taking a window, of looking at just a small window, is that when you take a small window, effectively what you're doing is you're multiplying your signal by a small pulse that's 0 outside the window and 1 inside the window. And when you do this, you are changing the frequencies in the signal. Now, normally when you're doing this, you would apply what's called a window function to your signal beforehand, which will cancel out these effects. But because of the way we're doing our DTFT, we can't do that efficiently, because you would have to multiply all 256 samples out with it for each sample that comes in to compute this. So instead, what we do is, and so you can see the effects of an uncorrected system right here. So the angle is a lot more unstable, and as the magnitude just goes completely crazy. You can still tell that it is a ping, but the magnitude swings a lot more wildly and isn't as stable as it was back here. And you'll actually notice that there is no red segment here, so our system did not detect it to be a ping. So to deal with this, it actually turns out that the time when the windowing effects are minimized inside of DTFT is when the number of samples in that DTFT is equal to a full wavelength. So I believe this is somewhere around like 17.75 wavelengths being fed in here. To calculate this, which is why we get all these weird effects. So to deal with this, what you have to do is look at your wavelength, or look at you pick some target sample size, buffer size. In our case, we use 128, and then round that number to the nearest full wavelength. In this case, the closest one that ends on an integer, or the closest one is 123 samples, which isn't exactly correct, which is why there's still some oscillations in the magnitude. But it's much closer than this, which is 128 samples. So that it's one thing that one of the small things that you need to consider when building your system. We actually had missed it in earlier versions, which caused some pinger frequencies to not work well. There are always a bunch of pitfalls in any complex system like this. So in summary, track mode, you have to choose your DTFT to match the frequency to deal with any windowing effects. And then you compute then you iteratively compute this on each element, and we store the phase difference as well for computing the variance. And then when we see that the magnitude is high enough and the variance falls below the threshold, and variance generally goes to basically 0, we then compute the heading. We actually take an average of the last 32 phase values just to have a little bit more stable heading. And then we notify the main computer that we got a ping, and here's the heading to it. And that all by itself basically solves the hydrophones problem. With that, you can find the active pinger and surface in the octagon and win the competition. But this assumed that you knew exactly what the pinger frequency is. You can guess fairly well, since I believe they tell you what frequencies are possible. You can just check each one to see if there is good data coming in there. But what we actually do is we have a second mode for our hydrophones called search mode that identifies what pingers are active. So this is where the discrete Fourier transform comes in, the DFT, because it looks at all frequencies, or a large range of frequencies, and will tell you about certain ones. So the particular DFT we're using, the particular one we're using looks at signals in 1 kilohertz steps. So we can say that, okay, there's a pinger at 25 kilohertz or 26 kilohertz or 27. And in general, so we put together chunks of 256 samples and then do take a Fourier transform on that. And then for all the frequencies in the range of possible pingers, you look to see if the magnitude is above a threshold, and if it is, the local maximum. And if it is, then that's a possible pinger. And then there is some method which is used later to compute what the best, or to choose a best pinger out of that. There's a lot of ways you can do this. I believe ours is we repeat this algorithm like 5 or 6 times and then pick whichever pinger shows up the most often. Because you can, when you do this in real life, you can get random bits of noise that show up, and for 1 or 2 runs will show up as a ping, or show up as high enough magnitude to register a ping. So here's a graphical representation of that DFT. We run this over a period of 1.2 seconds usually, and any pings that show up during that will be declared a ping, at least for that run of the algorithm. And then the computer will aggregate all of those to choose an actual pinger. So all this yellow area is random noise. The x-axis here is time, and the y-axis is frequency, and then the color represents how strong that frequency is. So as you can see, there's these little red spots once in a while. Those are the pings actually occurring. And so most libraries have any signal processing library will have a Fourier transform function that outputs data like this. but it's not going to be in nice, pretty graph form. It's in numbers. And so you can look at the numbers at a particular time. And so on the bottom left, there is the graph of frequency versus magnitude for a time when there is no ping going on versus top right, which has an actual ping. And it shouldn't be terribly difficult to write an algorithm that identifies those peaks. It's a fairly simple problem. And that is search mode. That's basically all of it. Just looking, run through each of these 256 sample periods and identify any pings inside them. And with that, that's how you build hydrophones. I'll stick around for a bit to see if any questions roll in. But yeah. All right, well, I guess I'm going to call it quits now. So I will be happy to answer any questions over email later. But for now, I guess I'm signing off.